So this is our final chapter, chapter 9.5 for the course, and it's all about comparing two population means. So we're going to go through the process of doing that, conducting hypothesis tests, and constructing confidence intervals about a population mean for independent and dependent samples. Now, what do we need to know here? How to determine whether a sample is dependent or independent. People chosen in random samples are asked how many minutes they spend reading and how many minutes they spent exercising during a certain day. Researchers wanted to know how the different mean amount of times were for each activity. Is this a dependent or an independent sample? Here's another example, and we're going to discuss these examples in a second. A sample of men and women each had their hearing tested. Researchers wanted to know whether typically men and women, men and women, men and women differed in their hearing abilities. Is this independent or dependent? So, third example, a random sample of married couples are asked how many minutes per day they spent exercising. Means were compared to see if the means exercise time for husbands and wife differed. Is this dependent or independent? So in the first case, in the reading and exercise example, the samples are dependent. Okay, in this one here, the samples are dependent. Okay, and the reasoning, the study was based on one sample of people who were measured twice, once per reading and once per exercise. Now, in the case of the hearing, a sample of men and women each had their hearing tested. Researchers wanted to know whether typically men and women differed in their hearing ability. The samples are classified as independent because two different populations were used. See that? In the first case, the same population of use. In the second case, two different populations are used, one for men and the other for women. The people were not related. The third example, a random sample of married couples are asked how many minutes they spent exercising. Means were compared to see if men exercise times for their husband and wives are different. In this sample involving exercise of married couples, the sample is dependent because each husband is paired with his wife when they compare the results. Okay, so the third one is a little tricky, but you can get it. Now, to construct confidence intervals for sampling for differences in population means giving independent samples and checking, given independent samples, checking three conditions. The three conditions have not changed. The samples are random samples and independent. I don't know what's wrong with this today, but the spelling is so bad. Independent. Both samples are randomly taken from their population and each observation is independent of the other. Next, the samples are not paired. Independent samples, and that's specified already. And finally, large samples, the populations are approximately normal or sample size are each 25 or more. Okay, so either or has to hold for large samples. And this is when you want to find confidence intervals for independent samples. Now, interpreting confidence intervals for independent samples, U1 minus U2. Interpreting confidence intervals for the difference of population means given independent samples is the same as interpreting confidence intervals for differences of population proportions. If 0 is in the interval, very important, there is no significant difference between mu1 and mu2. Okay, that is important. If 0 is inside of that interval, let's say it's between -7 and mu is between this is mu, or better yet, let's say mu1 is -7 and mu2 is +3. 0 is in that interval because 0 is a number between -7 and 3. There is no significant difference between the two. Okay? If both values in the confidence interval are positive, then mu1 is greater than mu2. Okay? So if both are positive, then mu1 is greater than mu2. Could be, say, mu1 is equal to 11 and mu2 could be equal to 3. 11 is greater than 3. And that's if both values in the confidence interval are positive. Okay? If both values in the confidence interval are negative, then mu1 is less than mu2. Okay? That means that mu1 could be, say, -11 and mu2 could be equal to -7. So mu11 is less than mu7. -11 is a smaller number than -7. College randomly surveyed day students and evening students to determine the number of units students were enrolled in. The data is shown in the table below. Use the data to find a 95% confidence interval for the difference in the mean difference in the number of units for the two groups. Based on your confidence interval, is there any difference in the mean of the number of students taken by day and evening college? So here we have in the day, number of students surveyed was 72, number of students surveyed for the evening was 68. Mean, standard deviation, standard deviation. Check the conditions, random sample, samples are independent, and large sample, okay? Now, this is generally done using StatCrunch, especially if you have a lot of data. StatCrunch, you would simply do two sample T summary or T data, whatever it is that you're doing. Put in your sample mean, sample standard deviation, and sample size for the first set of data. Sample mean, sample standard deviation, and sample size for the second set of data. Take your confidence level, and it gives the confidence level as 1.66 to 3.94. That's the confidence interval for U day minus U evening. Since both values are positive, we know that U day is greater than U evening. Okay, remember what we said. Okay, that that this means that the first mu is greater than the second mu if both are positive. Day students enroll on average in more units than evening students at this college. Mu2 is greater than mu evening. The difference in the mean of the numbers in units enrolled is estimated between 1.6 and 3.94. I put the instructions here if you wanted to try this with the TI-84, but I'm going to do these using StatCrunch because it's a whole lot easier doing this in StatCrunch. Now, what are some of the problems happening here? So let's look at some of these problems that we have here. The accompanying table shows the technology output for a two-sample t-test. Okay, this is this table below here. For the number of TVs owned in household of a random sample and students at two different community colleges. Each individual was randomly chosen independently. Okay, I want you guys to see that that's making the claim for normal and the conditions are met already. Okay. The students were not chosen as pairs or in groups. They specified all of this. One of the students is a wealthy community. One of the schools is a wealthy community college, and the other is a less wealthy community college. Complete the steps to test the hypothesis that the mean number of TVs per household is different using a significance level of 0.05. So, what you want to do here first is to make sure that you know that the null hypothesis H0 is mu the wealth the less wealthy is equal to the more wealthy. Okay. Equal to the more wealthy. And then the null hypothesis would simply be the same thing, not equal to the more wealthy. Okay, not equal to the more wealthy. Okay, now, so for this, you would want to do a two-sample t-test. Okay, two-sample t-test from independent samples should be used. The random sample condition applies. I'm taking the answers from down here. All three of these conditions applies to the test and holds. So if you're selecting in the drop-down box, it will be this answer here. All right. Now, the next thing they're asking here, we're trying to determine everything they're asking is the significance level that's given in the problem that we're comparing to, 0.05. So you can put that number in there, 0.05. 0.05. All right. The t value comes from this table. Okay, the t value right there, 1.05. And the p value is 0.0. Yeah, I was right, 0.300. Okay, both came from the table printout here. Since 0.3 is greater than 0.05, okay, do not reject, okay, do not reject HO at the 5% significance level because there is insufficient evidence to conclude that the mean number of TVs in the wealthier community is different from the mean number of TVs of students in the less wealthy community. Now, the confidence interval would come from our technology output, negative 0.365, 0.365 to 1.165. Okay, on a number line, we have 0 here, we have negative 0.365, and we have 1.165. So this interval captures 0. This implies that it is plausible that the population means are the same. Okay, plausible that the population means are the same. So you're going to get all the answers from down here. The population means are the same, and the others is captures. What else? Insufficient. Do not reject. All three of these are applied to the test. Sorry, applied to the test and holds for all three answers here. Okay, that didn't come out right. Let's do that again. Let's just mark it with a T. This applies to the test and hold, apply to the test and hold, apply to the test. All right, now this one we didn't have to compute any data. The data was already provided to us. Now, we're going to go deeper into this and look at the case where the data is not provided to us. I'm sorry, where the data is provided to us, okay? So let's go ahead here. You would have that nice little button to move the data to that data that you're given, that you can move it directly to StatCrunch, okay? A random sample of male college baseball players and a random sample of male college soccer players were obtained independently and weighed, two different populations. The accompanying table shows the unstacked weight in pounds. The distributions of both data sets suggest that the population distributions are roughly normal. Determine whether the difference in the means is significant using a significance level of 0.05. So we know that this is not less than or equal to. This one is equal to, and this one is not equal to. The mu baseball player is equal to the mu soccer player. That's the null hypothesis. Not equal to is the alternative hypothesis. Now, you want to go to StatCrunch. I've already moved this data to StatCrunch, so I'm going to go to StatCrunch here. Okay. And I have my baseball and soccer in the first two columns here. Now, stat, T-stat, to sample with data. Okay, look at that sequence with data. Column 1, I'm selecting baseball. Column 2, I'm selecting soccer. The hypothesis equal to 0. Okay, if mu1 is equal to mu2, then mu1 minus mu2 is equal to 0, or mu1 minus mu2 is not equal to 0. Okay, and compute. So I'm going to snip this, put it over into our notes, and we're going to let's move this over here. New. And put it over here. I'm going to have to drag this in when I get it here. So all right, so here we go. So the t value to 2 decimal places is 5.05. And the p value to 3 decimal places is 0.000. What is the conclusion here? So 0.000 is less than 0.05. Okay, reject. We have to reject the null hypothesis if it's less than. at the 0.05 significance level, there is sufficient evidence to conclude that the difference in mean weight is significant. Okay? In other words, we are going to reject the null hypothesis and go with the alternative hypothesis, that there is sufficient evidence to conclude that the difference between the mean weights is significant. Okay? FYI, what I was trying to explain here to you, if that for these two here, if mu1 is equal to mu2, this means that mu1 minus mu2 is equal to 0. Okay, and then if mu1 is not equal to mu2, this means that mu1 minus mu2 is not equal to 0. That's why we got that terminology right there. Okay? All right, more fun stuff. So look at number 3. A random sample of male college baseball players and a random sample of male college soccer players, same type of data, but see what's happening here, same type of data, were obtained independently in weight. The accompanying table shows the unstacked weights in pounds. It might seem like the same question, but we have to be careful about what it's asking, okay? The distributions of both data suggest the population is normal. Use a two-tailed test with a significance level of 0.05 and a null hypothesis that means the weights of soccer players are equal is rejected. Okay? Now, what is the 95% difference, confidence for the difference between the means? Would it capture 0? Coming back to our notes, okay, remember we spoke about this capturing 0, and I want to go back to see what it says. If 0 is in the interval, there is no significant difference between mu1 and mu2. So we go back to the answers here and we look to see which one expresses that thought. Okay? And I believe it's this one. The 95% interval would not capture 0. Wait, am I in the right one? Yes. Would not capture 0 because the hypothesis that the mean weights are the same is rejected by the hypothesis test. Now, how do we know that? How do we know that? So we're going to do that test in a little bit, okay? But again, understanding what this means, the 95% interval would not capture 0 because the hypothesis that the mean weights are the same is rejected by the hypothesis test, right? Remember we said that. The null hypothesis that the mean weights of the soccer players, let me kind of highlight that for you to see what it says here. That hypothesis is already rejected, which is why this answer is a good answer. Okay? Now, if a 90% confidence interval for the difference between the means is found, would it capture 0? What do you think? It would still not capture 0, okay? Because a 95% interval is narrower than a 90% interval. The only difference is it's now a narrow interval and centered at the same value. Based on the results of the hypothesis test, a 90% then would not capture 0 also, okay? Because they're both at the same center, so it wouldn't capture 0. the center doesn't change. Okay, so 0 cannot be, by reasoning, 0 cannot be in a 90% confidence interval. And if we choose an 80% confidence interval or a 50% confidence interval, that um, that middle value here, whatever that is still at the same place. The only difference is the graph is getting narrower and narrower as we decrease the confidence interval. So now we're going to find a 95% confidence interval for this data, and we're going to use StatCrunch for this again. So let's go to StatCrunch here. I have the data solved in baseball 1 and soccer 1, so I'm going to go through the process again with you. Stat, tstat, to sample with data, baseball 1, soccer 1, and I'm taking a confidence interval this time. Okay, confidence interval. So I don't need to put in anything else, of 95%. Compute. All right, and let's clip this out and paste it to our notes. All right, here we go. So this is, they want this to what? How many decimal places? 2 decimal places. So 11.73 to 26.27. Okay, 26.27. That's these two numbers right here, 11 and 26.27. All right, so notice this interval does not capture 0. And what does that mean? It shows that if you think about it, the mean weights, it shows that the mean weights for soccer and baseball player are significantly different. Remember, it would not be significantly different if it captured 0. But on a number line, 11.73 to 26.27, 0 is somewhere across here. So 0 is not inside of this interval here. Okay, that means that the two results, the two means, are significantly different in this case. Okay, and here it is. That's actually the significant difference right there, 19. All right, question 4. The prices of sample books at a university A were obtained by 2 statistics students. Then the cost of the books for the same subjects at the same level were obtained for University B. These are paired here. All right, they're paired. They're attached to each other. They're paired. That's going to be important when we do a calculation here. P-A-I-R-E-D, paired. If you think back to example 3 above with the husband and the wife team, that's what's happening here. Assume that the distribution is normal enough to proceed, and assume that the sampling is random. First, find both sample means and compare them. All right, so again, I've used StatCrunch here, and I put the data in 2 separate columns. I put it as University A, University B here. I'm going to find the mean, you can use perhaps a 1 sample summary, whatever makes you happy, or you can use the calculator, normal, and so on. Okay, we just need to find the mean for that. with data. So we need for University A, compute, and I can see the sample mean here is 68.8667. Okay, I'm going to copy that and insert it over here. Okay, so I have my sample mean for the first sample to 2 decimal, the nearest cent, so 68.9, yeah? 68, I'm sorry, cents, so 2 decimal places, 68.86. 68.87, that's dollars per book, yeah. And I can take the second set of data. So I'm going to go back to options, edit this, and take it for University B instead, compute it, and I can see that the sample mean this time is more. Sample mean for this case is University B is 72.87. 72.87, yeah. So copy that, bring it over here, paste it. Okay. All right, so this one is 72.87. So obviously the sample mean at University B is larger. Okay. To set up this, then the difference between University A and University B would be we're looking for one with equal and not equal. This is the only one with equal and not equal. Okay, the difference is equal and the difference is not equal. Now, to get our t-stat and p-value, we would have to, by the way, this is highlighted here as the sample mean. Let's go ahead and compute, ask the StatCrunch to compute the rest of this, okay? So now we want to do the whole t-stat, and at this time you don't want to do one sample, you want to do paired, okay? Because we're talking about the same type of textbooks for the same courses, but at 2 different universities, so paired. Column 1, University A, column 2, University B. Hypothesis equal to, not equal to in compute. Sorry, this is backwards. Let's do it one more time. Stat, t-stat, paired. Okay, University B first this time, and then University A when we pair them, okay? And compute. There we go. Okay, because in this case B is larger than A. Understand that B is larger than A, so I wanted to put B, University B minus University A, in order to get that positive as the t-stat. Okay, I'm going to paste this over here and then drag it in. Here we go. So the t-stat here is 3.2 decimal place here, 3.16. And the p-value to 3 decimal places, 0.007. 0.007 is less than 0.05. So we have to reject the null hypothesis. Reject the null hypothesis. There is evidence that the mean difference is not 0. Okay, remember we're always talking about being 0 and not 0. Make sense? reject HO. If it was greater than, you would not reject. All right, the other two questions, you can probably do them on your own. A 95% confidence interval is equivalent to which of the following? That came from your notes. Two-tailed test with a significance level of 0.5. Okay. A confidence interval answers which of the following questions? What is the estimate value and how much uncertainty one does this have about the estimate? Okay. All right, we are going to stop this video.